Hi, hello, my name is Eliška. I'm gonna have a talk about this long buzzword, which is a topic of my research. So I'm a researcher. This used to be my side quest, which kind of happened to be my main quest since this year. My background is that I'm used to be a software developer. I guess I still am, but now I'm developing software for quantum computers instead of the classical ones. During this talk, I'm gonna try to explain this research area I'm working on, so it's a little bit more understandable at the end. So the first of the words in the title, quantum. I'm gonna try to give a brief introduction without going too much into physics or any mathematical details. So let's start with a question: what is a quantum computer? I would describe it simply just a different type of computer. Groundbreaking, I know. I would say let's ask a different question. What is a classical computer? You don't have to answer. It's a machine for processing information, very simply. It can have all kinds of forms. For example, this could be a computer as well, just a tiny one. What does it mean? What is a unit of information? In classical computers, it is something called bit. It can have two values, 0 and 1. And on the tiny information theory level, you can operate this unit of information by some logical gates. Why am I talking about it? Because of one important thing about classical computers. When the information flows through this machine for processing information, we call it a computation, and the important part is that this computation has a predictable deterministic outcome. What does it mean? When I take, for example, the AND gate, I know what the result will be based on the values of the bits I put into it. It's not like that sometimes AND will give me a result of something and other times of something else based on the same input. It will always be the same result, and I can predict it. It won't change. Remember that. Quantum computer is also a machine for processing information. The only main difference is that it processes this information a little bit differently. It also has some units of information. We just don't call them bits. Let's say we call them qubits, but it's not like the only type of the unit of information we can work with quantum computers, but qubits are the most famous ones, so I'm gonna refer to it as qubit. It also works with some logical gates. We call them quantum gates. They also somehow are used to make the information flow through the machine. And the difference is that computation in quantum computer has a probabilistic outcome. What does it mean? When I take whatever quantum gate and I use the same input, I don't know by 100% probability that the result will be always the same. I don't know it. I can predict it with certain probability. Sometimes the probability is higher, sometimes it's lower, but the main thing is that I don't know it. And I know it only after I measure it, which means I look into whatever where the output is stored and I look at it, and that's the measurement. This is important because this behavior of quantum computers allows us to do kinds of different types of algorithms and computations we can or can't do on classical computers. And that's it. That's all you need to know about quantum computers, I guess. That's the main difference. I guess mainly for people, especially coming from security background, if you heard about quantum computers, usually you heard about them in context of some bold statements such as that it will break RSA or I don't know, whatever cryptography algorithm. that, I don't know, it will be much more powerful than classical computers, and so on and so on. My answer to that is that it's good to be prepared, I guess, but we are not there yet, and we probably won't be there, I guess, in the next few decades, at least. But we do have quantum computers already. They are called NISQ devices. That stands for Noisy Intermediate Scale Quantum Devices. What does it mean? These quantum computers can do certain stuff already, but they can do these advanced quantum algorithms. For example, they can't break the factorization yet, but we can do stuff on them. They are mainly interesting mostly for physicists, not for computer scientists, but they're cool. That's how I would summarize them. They're at least cool for me, that's why I do research on them. This is just an example how certain type of quantum computer can look like. Example how it usually looks to me, just like some UI interface where I can read stats about the quantum device I'm working with. So first, buzzword uncovered. I didn't want to spend too much time on that because I guess that you are not that much interested in the quantum part solely. The second one is machine learning, specifically quantum machine learning. Also, just some brief introduction. It's one of those research areas which is interesting on that quantum computing hardware we already have available. It can be divided into two main research paths. One of them are variational circuits, the second one are kernel methods. I focus on kernel methods. Currently, usually the state of these quantum machine learning algorithms, how does it work, is that they are hybrid. What does it mean? That certain part of the algorithm of training the model, or not training, preparing the model is done using quantum hardware, and a certain part is done using classical approach, aka classical computer. Just briefly touch on the kernel methods. I guess most famous example of kernel methods is a machine learning algorithm which is called support vector machine. What it does is it can be used for classification. Main part of the SVM, why it is in the kernel methods category, it's a function, just a mathematical function, which we call kernel function. And what this kernel function does, it's used for quantifying the similarity between samples. What does it mean? In classical machine learning, whatever machine learning, when I want to do some classification task, which means taking a sample and putting it into some class, into some category. I have some data set and I have some samples in the data set, and I want to know how the samples are different or similar to each other. And the kernel function is one of the ways how to measure it. We have all kinds of kernel functions. And in the classical machine learning, the only twist is that in quantum machine learning, we also have some types of kernel functions. The difference is that I just replace the kernel function with quantum kernel function. I use it in the same machine learning model, and then I work in the same machine learning workflow. So just the intro into the second buzzword, the machine learning. Now, the malware part. What is malware detection from a point of view of machine learning? Or from whatever point of view. It is a simple task to which we want to have an answer. The question is the sample a malware? And the answer is yes or no. What I mean by sample? In my case, with what type of samples I'm working with, I have some binary file, some executable file, and I want to know, is this executable file somehow malicious? Also depends on what do we define as malicious, but let's say we know how to answer it based on whatever criteria we are choosing from. And the question is, when I have this definition of what malicious is, how to answer this question. And in classical malware detection, I can do it through multiple ways. Either I can be some malware analyzing person who takes the binary, the specific sample, do some reverse engineering maybe, or some whatever type of analysis, either static or dynamic. I can try to run the sample in some virtual environment, watch how it behaves on network or in the computer system, and based on that, at the end, I can tell, okay, this is malicious or not. That's one of the approaches. Or I already know this sample, so I have its signature. I can get this signature either by that this specific person looked into this specific file themselves, so I can have this signature that it is malicious based on whatever different approach. Maybe I can automate it somehow, or it is similar to something I know that it is malware. When I want to automate it, I can use machine learning because we have a lot of malware samples, so it is impossible to go through each of them by hand, that some specific person looks at it. So we want to naturally somehow automate it, and that's where the machine learning comes from, and that's how it usually works in like modern malware detection software. How it connects to my pipeline, my quantum machine learning pipeline. I have some malware dataset. I pre-process it somehow because I cannot take this general binary file and just put it as an input into the algorithm. I somehow have to describe it, extract some features from it. That's a research task on its own. How to take this giant binary and extract important information from it. So I do it somehow. Then I use the quantum computer just for this specific part of the computation, which is that I compute the kernel function for each of the samples in the dataset. And I put it into some kernel matrix, and I put it into the model and train it classically, and then I have some model which can answer this question, so evaluate the performance. Why even bother with quantum approach? Why just like not use the classical machine learning? At least two different approaches how to look at it. When we are coming from the why I have classical approach and why bother with quantum. If I would be interested just in classical malware detection, that means just answering the question, is it malware or not? The most basic argument I could give is well, we have a giant data sets of malware samples because we already have collected a lot of malware samples through the years. I can just use some deep learning, neural network, whatever, just some classical machine learning approach to process it, and I don't have to bother with the quantum approach at all. And I will get pretty nice results. But if I look into a more niche part of the problem, is that I'm not maybe interested just in answering general, is this malware or not? Maybe I'm asking, is this malware from a specific malware family? Does it fit into some extra categories? Is it a good sample for adversarial learning? Then the size of the data sets I have available reduces dramatically. So I'm working with a smaller data set on which, even in classical machine learning, I wouldn't use the classical deep learning approach, and I would be interested in other models. One of them commonly used is the already mentioned SVM. And because the SVM is based on this kernel function, which measures the similarity, even in classical SVM, we want to explore different types of the SVM based on that kernel function. So naturally, I would be interested in exploring also the different types of quantum kernel functions. The idea is that the quantum kernels could capture some structures classical kernels can, based on the way how they use or exploit some of the more physical quantum properties of the computation. I won't probably go much more detail into this. The general idea is that we want to use something which is hard to simulate classically. Why I? Specifically, what was my motivation to work with the quantum machine learning for malware detection? As I said, my background is just like classical computer science and computer security. And when I was in my last year of master studies, I was like, I have to do some research for my master thesis. And I studied security, so I was like, okay, it has to somehow fit into the computer security area. But I also was like, but these quantum computers, they are kind of cool. How could I combine it together? So I was looking for something which can combine these stuff together, which was the machine learning, quantum machine learning for malware detection. That's my specific case, but that's how it also usually goes in industry when you do quantum computing research, not in the academia field, but in industry. In industry, we are also motivated by not so much having like mathematical proofs that this quantum machine learning approach is perfect for everything, or for like prove that it's perfect for something. It usually goes from the other way, which is you start with like some experimental idea and you try that approach for it and see if it works, and then you wonder why it works. That's also the case in classical machine learning. Sometimes we have those, for example, large language models, which are very popular right now. Sometimes we also don't know how they exactly work, why this large language model is capable of doing the stuff it does. We have some ideas, but we are not sure. We just experimentally proved that it performs somehow better, but we don't have like those mathematical proofs of what it does, and that's the same approach here. I hope I haven't bored you too much yet with the theory background. Hacking quantum computers. For this talk, I was kind of thinking about like what my audience here is going to be, and actually it reminded me this question I sometimes get from my colleagues from the security department I'm working at. Is like just like some philosophical idea, like could we somehow also hack quantum computers? And first, when I heard this question for the first time, I was like, I don't think we are there yet. We don't even have like industry-ready quantum computers. Why we would be interested in hacking them? I would say my question to that is, as I kind of realized when I was preparing for this, that it's actually already happening, but it's not a bug, it's a feature. And I'm gonna explain what does it mean. It's the software. So, as I mentioned, we already have quantum computers available. One of the main players on the market is the company called IBM, which has the most advanced quantum computers for industry applications. What does it mean? It's not just like some machine in the lab which only specific scientists which go to the lab can use, but it's something which researchers, for example, someone like me, can use even though I'm not in the lab directly. I can easily access it through cloud, run my computations there. How to operate with this quantum hardware is through the software. The software is called Qiskit. It's so this part of the talk will be kind of specific to these IBM quantum computers. I just want to mention that they are like not the only quantum computers. Like IBM is not the only company which has quantum computers, but it's like the most large-scale industry application. That's why I'll be focusing on it. So the software to operate with this quantum hardware, it's called Qiskit. It's a Python SDK. It's open source. It was originally developed or introduced by IBM. Certain parts of the Qiskit SDK are still maintained by IBM, but it's mainly a community project because it's open source and it's mainly maintained by the community, not by the IBM as a company. It has many flaws. The first one is that it's something which is not production ready, which is pretty bad when it's the main SDK for operating real quantum hardware. The second flaw, which I named as over-engineered but under-maintained and written by researchers, not software engineers. I see someone already taking pictures. I will then make the slides available. Maybe just one more disclaimer. I usually say that I'm the biggest Qiskit fan, but also the biggest hater. So what I mean by over-engineered, by under-maintained. Qiskit, it's the SDK itself. It consists from many separate Python modules. Some of these modules, some of them are maintained by IBM or developed by IBM. Some of them are maintained by third-party companies, some of them by community. The main problem, what I mean by written by researchers. Usually, even when IBM release new Qiskit Python module, it is heavily problem-oriented, not software-oriented. Example, I was at IBM Quantum Developer Conference just 2 weeks ago, and they introduced a new module for optimization problems. It's called Qiskit Optimization, and it should help the researchers which do optimization tasks on quantum computers. It is it is like all the classes, everything in the module, it's very specific to the optimizations problems. That means that it's like, for example, you have functions or classes which has tons of very specific problem parameters, which I don't know how much you are into just classical software development, but like just in terms of like reusability. If you want to reuse the module or the classes for something else and some specific problems, it's already making it kind of hard. Usually in all of these modules, they introduce some specific structures, specific things which are very tied to that certain module, which then makes it problematic when you want to connect it with other stuff from other modules, which is something you usually want to do when you write the code for the quantum computers. That also ties to inconsistent behavior. So when you want to connect somehow the stuff from different modules together. And also the main problem, constantly changing API. What does it mean? IBM each year release a new version of Qiskit, which makes the previous version completely unusable. In terms of that, you have to like really completely rewrite your code. That happens every year, but they also have this release cycle every 3 months, which kind of breaks your code, a little bit less than the 1 year big release cycle, but breaks it a lot. That's a common problem. For example, when I was writing a code for my master thesis, when I started working on that project, so I finished my master thesis in May, and then I wanted to publish it as a paper, as a publication, and I finished the manuscript for that paper in September. So I finished my master thesis, like working on the master thesis in May, and I finished the paper, like the text for the publication and so on, in September. The code I had in May was already unusable in terms of like really I had to do like major changes to make it work again. Yeah, so that was a longer example of the flaws. Then I picked a few like more concrete examples, which I have on the slide here. The first one, it's called transpilation. What does it mean in quantum computing context? When you work with this Python SDK, it is still a very high-level way of how you write the code for quantum computers. So you have some Python code which somehow describes some operations on the quantum gates and so on, but it's still very high level, and you in this high level code work with, for example, some quantum gates which are not available on the end hardware you are working with. What does it mean? You have to transpile your code to the gates which are available on the hardware. I know I said like maybe a lot of buzzwords here again. To make a classical parallel, it's like when you write a code in C and you want to compile it for a specific hardware. Each hardware has a different set of instructions and so on, so the compilation for the specific hardware, like the machine level code, will be different. So this is kind of like a high level of compilation. So the transpilation itself, like this process, is you have tools in Qiskit to do it. The problem is that there is like not one specific way how to. The same way as like when you are compiling classical code to the machine instruction code, it's not like one specific way how you can do it. You can like in the classical compilation, I don't know, play with many parameters, and you will end up with different machine code to run on the end hardware. This is something similar. And based on all the optimization you want to do in the transpilation, you will get a different machine level code. The problem is that in the Qiskit, when you just use the library tools for it, they have a random seed in them. What does it mean? I wouldn't have a problem with the random seed itself, but the problem is that Qiskit in general lacks good documentation. And in terms of the random seed, I figured out after like 2 months after I like learned about like when I was learning to work with Qiskit, after I like learned about transpilation and so on, I was like wondering why the transpilation output is sometimes very different from what I would expect, because you can set some optimization levels and so on during the transpilation process. I found out that there is also some randomization involved, but if you want to fix the random seed in terms of you want to have something reproducible, which is usually very important when you do research, that you want to have results which are reproducible, so someone else can go and reproduce them. This random seed is hidden in a way that you won't find it as, I would say that random seed, which is like not fixed to something, I would say that something which belongs at the top of the documentation of functions like this, it is kind of hidden, and I think I even had to go into the source code itself to find it. That's also a very Qiskit approach, that usually it's better to go and find the source code than to read it from the documentation. Luckily, it's open source, so you can at least do that. So that's the transpilation thing. Another thing is many modules in Qiskit are maintained by third parties. That itself wouldn't have to be a problem, but it is a problem that in terms of that many of these modules are only usable for simulators and unusable on real hardware. Because just like explain the difference, when you're developing some quantum computing code, you first want to debug it on quantum computer simulator, because just like debugging everything on the hardware, it's expensive, yes. So you first debug on a simulator and then you run it on real hardware. The thing is that whole libraries are completely useless on the real hardware in terms of the implementation, to the level that, for example, when I started working on this project, I was like, okay, so there is this Qiskit machine learning library. It's pretty famous, heavily used. I could use it. I don't have to write everything from scratch. So I used it, I debugged it. First run of experiments I did on simulator, and I was like, okay, everything works as it should. Now it's time for the real hardware part step. I figure out that just taking whatever I have and try to use it in another module, which is responsible for the transpilation, I cannot use these modules together because the Qiskit machine learning library is like completely like how to say it, they just can't work together. What that means for me is that I had to fix the machine learning library myself, which the fix itself, it's like not something that you go and change a few lines of code. You really have to go into the source code, identify what specifically you have to fix. You have to figure out how to fix it. This process took me another 2 months just to make the library work on real hardware. Another example of flaws by design. So there's this thing, it's called IBM Quantum Platform. It's, as I already mentioned, there is this module called Qiskit IBM Runtime, which is responsible for the transpilation and for the communication with the real hardware. In Python, it's through this library. In like more UI type of point of view, it's this website. It's called IBM Quantum Platform, where you can access your computational jobs and so on, which runs on the hardware. This whole library has many flaws. My favorite one is are blocking functions for computational jobs. What does it mean? So to run the code on the real hardware, you have to send it as a request, right, as a computational job to the hardware. In that computational job, you want to do whatever, compute whatever, but you are not the only person using the hardware, which is somewhere in a lab in US. So your computational job has to wait in some queue. Depends on the whatever contract you have with IBM, if you are using the publicly available access, or if you have like special contract which is paid, some paid license, you have to wait a certain amount of time in the queue. When you have this blocking function which sends your job, the whole time you are waiting in the queue for like running the job and for the job itself do the computation, the function like won't return. Like, you have to make the program run the entire time you wait in the queue. And you can wait in a queue for like a few minutes or for a few days, for example. So what does that will mean? You have to leave your computer, whatever, opened. You have to make the program running until the function will return. But you need it to be returned because, for example, you want to get the ID of the computational job or whatever. Because just like some parameters about the computational job, you won't get it until it returns, until it gets computed on the end hardware. So if you want to fix this, you will have to fix it yourself, which, for example, that's what I did when I was fixing the library. If you won't do it, you have to wait. I guess I don't have to go deeper. It's just like not a good idea to leave blocking functions for stuff like just returning the job ID while it's waiting in the queue. It's like, I don't know, parallel to you send whatever task to computational server, and the whole time it's waiting in on the server, you just have to run the program and wait. Now, I have a more philosophical question. What is malware? Huge switch, but bear with me. I actually went to, when I was working on that master thesis, at the beginning there is like some theoretical introduction to the thesis, and I started with a section about what is malware detection, and so on. So I actually went and checked what I wrote there. There is like not one single definition of what malware is, but why I liked these two things I had there, I would maybe wrote them a little bit differently today. But what is malware? It refers to any software intentionally designed to cause a harm to a user, and it often affects computer systems without the user's knowledge or consent. Now, you can imagine what is this? Who is average user of quantum computing hardware? Usually, it's someone who is a quantum physicist. It's not usually any software developer, not a computer scientist. Usually, it's like some theoretical physicist or experimental physicist. I don't know if anyone in the room is a physicist. Is anyone in the room a physicist? Or do you know any physicist? How good are they in writing software? I don't want to like stereotype, but like I guess you kind of get the idea that like it's not their main focus. It's like from the name of the like physicist. It's someone who understands physics, not software. But quantum computing in general is just a field which combines physics and information theory, so classical computing. You have all these amazing quantum researchers who has this amazing theoretical research which they would like to somehow make it run on the real hardware. For that, they rely on the software. When you have a software which by default is very you've seen it yourself, and you have a person who already is, I guess, in like a good scenario, like average physicists who do software stuff is someone who has some Jupyter notebook and they do some basic Python code in that. That's completely okay. But it's not someone who will go and look into the source code implementation of something. They rely on the software working really well because they want to do something very specific related to the research area they are working on. Python is very common programming language for all kinds of people doing computer science or for physicists in other fields as well. When, for example, I don't know, when you are using, for example, scikit, which is a library used for machine learning, people who do classical machine learning, like the scientists themselves, they are also usually not pretty good software developers. But the difference between scikit and qiskit is that scikit by itself is a good library in terms of you can rely on it, that it does what it should be doing. So you can use it for whatever you want to produce as a code, but you don't have to go and fix the scikit itself. So the average user is a physicist who doesn't have this skill. Why I highlighted the bold words intentionally designed to cause a harm to a user? I don't think that qiskit is intentionally designed to cause a harm, but also a philosophical question is also like not intentionally designed to not cause a harm to a user. And it causes a lot of harm to a user. The second thing is, without the user's knowledge, that's also a very common example, as a common case as I introduce on these examples. So to answer the original question, hacking quantum computers, yes, it is possible, but you are targeting the developers, not qubits. That means you don't have to target the end device, which is some quantum computer in some probably like highly secure lab in which only very specific people can get in. If I would want to hack a real quantum hardware device, I would have to get to some city in the middle of nowhere in the state of New York, where the IBM research center is located. I would have to get in somehow, or I don't know, nuke it or something to destroy it. But I don't have to do that. Because if I want to hack the research being done on it, the weak spot is actually the software, the operating thing in it. If you are someone who is a qiskit developer in terms of like being in the community, which adds new code to the qiskit software itself, I think pretty easily you could hide whatever malicious code in it, and I don't think it. If you would do it in a slightly clever way, I think it wouldn't be discovered. I'm not giving any hints. I'm just saying that that's the stage we are at, and you don't even have to do that because it's already it's already working against the researchers. So we have these quantum computers, which are very pricey, billion-dollar machines, but we have a very fragile software which is operating on them. And the last line, that average physicists will never suspect software being wrong because they already expect everything to behave randomly anyway. If you remember the slide at the beginning when I was saying that the computation on quantum computer is based on probabilities, this is actually like just a joke about that, because we are like quantum scientists, we are already like used to the fact that we can't exactly predict the outcome. One more story from like real life. So one of my colleagues at university, two colleagues, they do research in quantum chemistry. And they wanted to run some experiment on the real hardware, so they used qiskit and some optimizer from the qiskit optimization module to do the hybrid loop where some computation is done on the quantum computer and some computation is done on a classical computer. Qiskit in this optimization model, they have also implemented the classical optimizer. And this colleague, I was talking with him and he was like, well, the numerical simulations are much better than the results we are getting from the hardware. Like the hardware results are like completely random. And we are wondering like if it's because of the hardware itself or like because of the qiskit, where could be the problem? Because the simulations are much more better, which shouldn't be like, there shouldn't be like such a dramatic difference. And I was like, and what are you using for the classical optimization? And he said that he's using the optimizer from Qiskit. And it's sad to say, but I was like, okay, the first thing I would look into is the implementation of the optimizer in Qiskit. Because I'm 100% sure that whatever is there, it will be much worse than like if you take optimizer implemented in whatever other library, like a classical machine learning library or optimization library. But the thing is that this colleague, because he's a physicist, his first thought was like, okay, so there has to be something wrong with the quantum computation, not with the software. Just they won't even suspect that the software could be wrong. And I would end with the fact that I'm the average user. In terms of, I also been hacked by this Qiskit software, because as I mentioned, I, for example, spent a few months of my life just fixing the library, and a few months of my life just not being aware of the bugs in the library. And it happens consistently. I have to consistently maintain my research code, which is not something which is published, just for my internal experiments. With each Qiskit release cycle, aka those 3 months, I have to go and update heavily whatever I have. I'm being hacked constantly. The only difference is that right now, because I've been working in the field for 2 years, 3 years, I'm already aware. But I wasn't aware at the beginning. And especially at the beginning, it took a lot of my time, which I could invest in the research itself. And it took a lot of, so I was actually hacked because I was unaware. I was working with software which was working against me. And I already had a better starting position because I'm a software developer, so I knew where to look at. But many quantum researchers are not there. And I think that's the main thing which is slowing down the research in terms of the algorithms. Right now, we are at the stage when we have very fancy, amazing, cool hardware machines, quantum computing machines, but we can't do much applications on them because we don't have the tools to operate them. And just back to the research I'm doing, because I haven't said much about that, I kind of went a different path. I would summarize the progress is it runs on hardware somehow. And I hope that after this long section I gave, I hope you can see that it is achievement itself. It is such an achievement that when I went to that IBM Quantum Developer Conference, it was a conference for a few hundreds of people. It was in the US. It is something which is not super easy to get in. I would hope that I will meet with other quantum software developers there. It was the minority. It was the minority that when my research results so far are not anything groundbreaking, not at all. But just the fact that it runs on hardware, and I understand the hardware, and I can make it run on a hardware, already gives me such an advantage. Really, just the fact that I have stuff which runs on hardware already helps me a lot to get to the conferences. And back to that developer conference I was at, it was a conference for 3 days, and most of the talks were very research-wise, which it's nice, but I would expect from a industry-organized developer conference something more practical, something more oriented to the developers. Well, it was there was one talk in the Friday afternoon at the end of the conference. It was called Qiskit C API, a users group, and that's where all the developers actually met. It was just, I would say, I don't know, at max 40 people in the room from few hundreds of attendees of this conference. That's one thing. And the second thing is, which I guess it's the most funny of it all. So IBM is a huge company. They invest a lot into the quantum computing research and everything. How many developers you think they have in a house for for developing this in-house part of Qiskit code? Any guesses?
5.
Nice. It's about 10 people. About 10 people. That's like, and these people were at this user group meeting. So you have hardware, which like the hardware they have at IBM. That's why I'm a hater, but I'm also a fan because like the hardware, it's fascinating. We have this kind of technology, but then you have like 10 people who actually like cares about the software in the company. It's like I don't know. I have here an iPhone, so it's like if at Apple there will be I don't know how many people for creating the hardware, the iPhone itself, but then like 10 people for creating the software. So like that's the comparison. Yeah, so my code runs on hardware. That's already an advantage. Yeah, we are limited by a lot of stuff. So not much meaning for the practical use. That's why I actually went for a PhD because after that master thesis project, I was like, okay, I have more questions than answers, and I spent a year on it. Now I'm another year and a half on PhD, and the answers or the questions already like keeps growing. So not much meaning for the practical use yet. I hope we will get there one day. The question is if the use will be malware detection or whatever else. I would like to see some practical use of the quantum hardware we have already available, not just like those imaginary fairy tales of breaking RSA. Yeah, I have a publication about it. Yeah, I'm not that much proud of it, but I guess I'm a big critic of my own work. But yeah, it's for people in the community, it's groundbreaking just because of the hardware part. And yeah, that's it. Thank you.
Thank you very much. It was really interesting and awesome talk. And now we have some time for questions. So if there are some questions.
Mm-hmm.
Does LLM help you with maintaining maybe the code every 3 months?
Oh my god, I was thinking about adding one bingo slide. Well, I usually, I'm sorry, but I usually play a game with my friends with like what kind of buzzwords will also appear when you have these kinds of talks. Usually, I guess you remember, for example, when the blockchain was such a big boom that everyone was like, we are using blockchain for something, and it was just like some special database. Right now, that's why I was mentioning the buzzwords, because I think that quantum and AI specifically is also the popular buzzword, and the LLM is another one. How LLM, like serious answer to that question, I would say that LLMs helps me mostly in the forms of those LLM chatbots, like in terms of like I don't know, studying or like replacing classical Googling with asking the chatbot first.
And does it understand the code? Because there is probably not many.
You mean like if, for example, like stuff like ChatGPT or something understand the code, or?
Yes, if it can update the library to the new API.
I would say that this is the same thing as with any other like classical software development. Like the LLM can help you somehow in the development process, but you still need the person who knows what to ask, who knows like whether the answer or the fix is if it makes sense or not. Like it can help you somehow, but you still need to know like what to look for. That's the same thing as when I was doing like classical software development and I was using those LLMs. Like sometimes it can help you, sometimes it produces complete shit. Sorry, my language.
said that you see the timeline of the capability of quantum computer to be in decades. But I think that IBM is saying that they will reach quite a lot of qubits. From what I researched, based on what they published, probably in 7 or 8 years they should hack, for example, Bitcoin, just by having sufficient logical qubits, even though there is not a quantum computer with even just one so far.
Yeah, I understand the question. Another thing which I like to add to that bingo card is IBM roadmap. For those who doesn't know what it is, it's like this a roadmap, a plan of IBM when they will reach this amount of qubits for whatever. The joke is that the IBM roadmap changes also very often. With these predictions, in general, like it's like I don't know, making predictions by reading stuff from your hand. Like the closer it gets, the more the more you can rely it. But just a simple answer: no, I don't think that in 7 years IBM will have the quantum computer which will be able to break RSA. And if they would have it by the amount of logical qubits which are needed for them, I can't speak for the hardware, but I can definitely speak for the software, and I don't think that will be available in 7 years. Well, like really, it's not a joke. Like with Qiskit itself, I've been working for like 5 years. And it got a little bit better, but also got a lot worse in other parts. So if I would take the same scale of my experience I already have with the software, I don't think the software will be ready. And then it's also a question of like the research in quantum algorithms themselves.
There is a new quantum computer at IP4I in Ostrava being installed in these days. According to the documentation, it should have like 24 qubits. Is this enough for some practical experimentation, like with real malware, or it is just for playing with the quantum computation basic algorithms or something like that?
That's a really good question. Thank you for asking for that, because I actually haven't touched that at all. Yes, like in terms of just amount of qubits, you need very little for the practical experiments, for example, with malware or with whatever machine learning, because you do a lot of pre-processing beforehand. Basically, in approach I use, the qubits, you have like the qubits are tied to the feature vector you are using as an input for the computation. What is a feature vector in terms of machine learning? It is a vector which somehow describes your sample. So in the pre-processing, when talking about malware, you first take the binary, you extract some features from it. For example, feature can be, I don't know, some histogram of bytes in the binary, or entropy, or information about strings used in the binary, and so on. Each of these things can be a specific feature. The feature, you have to somehow encode it into some like a numerical way, how like you have to somehow unify all these features, and you put them one by one into a vector. And you take this vector and you can reduce its dimension. That's something which is like usually done also in classical machine learning. And you have a bunch of ways how to reduce the dimension, but you reduce the dimension and you won't lose that much information by this dimensionality reduction. And then you somehow have to encode this feature vector into a thing which is called a quantum circuit. And that's the thing which is being then run as the computation. And the quantum circuit itself, it can have only like few qubits, I mean like 10 to 20 qubits, and it will be enough. It depends on the encoding you use. The encoding itself, it's something which is also a research area itself, but luckily this is something more theoretical, and we have a lot of very usable theoretical ways how to, like, already usable approaches of how to encode the information into a circuit. And you could do it in a way that you can use, for example, just 10 to 20 qubits, and that would be enough. So actually for like, that's why machine learning is one of those like interesting research areas on these devices, because of exactly that. Because you don't need that many physical qubits for these experiments, whereas for these factorization and so on, you need to like tons of them. Yeah. Okay, I guess that's it. Thank you.